Good morning, everyone. Just a couple of reminders. So for our first midterm, which is on a Wednesday night, September 21st, just remember you need an iPad for the exam to take the test on. And if you don't have your own iPad, you can check one out from the university. So make sure to take care of that before we come up on that midterm. Another thing is that you need a specific calculator. So if you look at the syllabus, you have to have like a TI 30, 83, or an 84. So you need, some sort of TI calculator 30, 83, or 84, and any variety with these numbers. So just make sure you end up with the right calculator for the test. I know there's a bunch of other calculators that aren't these numbers that are very similar in function and should be allowed, but they actually aren't. So just be aware of this. The TI 30s are the ones that are cheap. So just thinking about that as we come up on that first midterm in about a week and a half from now. Okay, so let's get back into naming compounds. We are starting the process of trying to categorize compounds. We're in that first category still of ionic compounds. There's lots of different kinds of ions. We were just getting into some of the molecular ions last time, but let's come back to some of our conventions for naming simple atomic ions. So when we talk about atomic ions, this is just thinking about the charge that an ion is going to have based on its periodic table placement. So if fluorine's going to form an ion, the only possible ion would be F-, because it's one electron away from the neon count. So fluoride would be the simple IDE ending for fluorine having its one extra electron for that F-. And then for, let me write the minus and the F closer together. So F- would be fluoride. Oxygen's 2 over to get to the neon count. So we'd have O2- being the simple atomic ion of oxygen. So that's the only common ion of just one single atom of oxygen. Like we're not going to see a single O with a minus or a single O with a 3-. If a single O has a charge, it's going to have a charge of 2-. This would be the oxide ion. So it's just the root name of the element followed by the IDE suffix. And so then nitrogen being 3 over from neon picks up a 3- charge and would be the name nitride. So notice the simple IDE ending is just indicative of the atom with its atomic charge based on its periodic table placement. Carbon doesn't really form a 4-. We'd probably call it carbide if it did. We actually call something else carbide, but that's a whole other thing. And it's not really part of our naming. So if you've ever heard of like calcium carbide, it's really not C4-, just because carbon doesn't commonly form the 4- ion. So something else ends up taking that common name. That's really nothing to worry about. But I just wanted to mention that carbon not really forming that 4-. So we don't really name it in this kind of system here. And so then neon is that right count. So neon's not forming a plus or minus charged ion. We talked about last time about how metals on the left side of the periodic table are going the other direction. They're losing electrons to form positively charged ions. So there's also other types of ions that exist. We were getting into the sulfate last time, sulfur with 4 oxygens with a 2- charge. Just happens to be a common ion of sulfur that exists. So we saw this one last time. That for this ion here, we just call this one sulfate. And the way this kind of works is you go into nature and you say, well, for like carbon, what's the most commonly found oxygen anion? What's the oxygen count? What's the charge? And you kind of take note of that, and then you call that ion the 8. So the 8 ending is just for the given element. It's just its most common count of oxygen and that charge. We're not predicting why that's the case. You don't need to know, well, why is CO3 2- for carbon what we call carbonate? Why did this not go as, like, why is this not CO4 2-? Why is this not CO4 4-? Like, why 2-, why 3 doesn't matter. We're just trying to learn that 3 oxygen atoms attached to carbon with an overall 2- charge is just a common ion, and it's one that we call carbonate. Nitrogen's nitrate with 3 oxygens. So nitrate. Then we have phosphate with phosphorus. Also, the common ion of phosphorus, 4 oxygens, but with a 3- charge. Chlorine, bromine, iodine share these formulas here, where you can imagine having BrO3 minus and IO3 minus. I don't know why this screen keeps flashing. It's kind of annoying. But the chlorine is chlorate. I hope if I write the letter I'm thinking. Chlorate is the common ion of chlorine. So the ones here in the middle are those common ions that take the ATE ending. BrO3 minus would be bromine, so bromate. And IO3 minus would be iodine, so iodate. All those with ATE endings. And then the one thing that's nice with the nomenclature system is if you more or less memorize the ones in the middle, there'll be a summary slide that kind of reviews what you need to memorize. But if you memorize the carbonate oxygen count and charge, the nitrogen oxygen count and charge, the NO3 with a 1 minus, the sulfate, the 4 with the 2 minus, you just memorize those and you can name a bunch of other things off of those names. Like if you recognize losing one O atom, so if you lose one O atom off of each of these, if you go from 3 to 2 on nitrogen, so you have NO2 minus, that's nitrite. And we just take the ITE ending. So if you lose an O, you just change the ATE suffix to ite, to ITE. So we'd have carbonite for phosphorus, phosphite, sulfite for sulfate, but now with one fewer O. So if a formula has a different formula, it should have a different name. So SO4 2 minus, SO3 2 minus are two different ions. They should have two different names, and they do. And so just very systematic to name these. So then we have the chlorite. I won't bother writing the bromite or iodite, but they would follow suit. Now, it turns out that only chlorine and the bromine and the iodine do the full range where they can actually lose a second O, and we can systematically name losing the second O atom with the hypo suffix. So we lost an O off of chlorite, so we call it hypochlorite. Now, we could name, and there could be some examples maybe where you could say, well, what would you call SO2 2 minus? It just doesn't really exist, so we tend not to really use examples of things that don't exist. And we're not even trying to have you predict or even know what exists and not exists. We just want to be able to, like we said last time, go from formula to name, name to formula, without having to memorize the why those particular formulas are the ones that predominate. We're just taking for granted that these are the formulas that exist, this is what we're trying to name. This would be hyposulfite, but it doesn't really exist, so we end up really not using it too many examples. So you could name it, but if it doesn't really exist, why bother using it in examples? And then if you go the other direction, you add an O to a formula. So if you take the second O away, you just go hypo out in front. If you add an O, you add a per out in front. And so you're adding a per to the 8 ending because that's the ion that you added the O to. So if you add an O to the formula of chlorate, so go to ClO4 minus, this would be perchlorate. So we have two 8s and two ites. So we have chlorate, chlorite, and then hypo, and then chlorate, and then perchlorate. Bromine and iodine do the same thing, so this would be perbromate. Periodate for iodine. So again, if you add an O, you could do this to the other atoms. It's just not very common or even possible for some of them. But if you added an O to, say, carbon, it would look like CO4 2 minus. Probably doesn't exist. I've never seen it before. But you would call it percarbonate if it did exist. So we could name it. It's just not conventionally something that tends to exist. So you tend to not see examples with it. So you could, but probably won't see examples of things that don't really exist. So that's kind of the range of naming these oxygen oxyanions. There's actually one interesting set of ions ion that follows suit from this nomenclature system, and that's actually the oxide ion. If you think of oxide just being the O2 minus like we talked about, we've I think mentioned the peroxide ion last time. So if you add an O, you go per in front. So the O2 2- takes that systematic name of peroxide. So it's kind of interesting that later we'll call this kind of like a common ion that we just memorize the name of, but it really takes almost a systematic name from this oxygen anion nomenclature system that we're developing. And there's another related ion that doesn't really follow suit from the nomenclature we just learned, but if you take a charge away, if you notice all the ions in this chart have the same charge. Like the chlorate series all have -1s, the phosphites all -3s. So when we're changing the O count, usually we don't change the charge. Oxygen's a little peculiar, and then it can form this ion here, and this one we call superoxide. Presumably because it's a super ion, I don't know. Must be really cool. It's actually really hard to form, and it's kind of peculiar in some of its properties. But it's just something worth noting in terms of like naming the charge. It's one of the few cases where we're like actually changing the charge. For the most part, sulfate, sulfite, both 2-, nitrate, nitrite, both -1s. But then peroxide, superoxide, both -2s, superoxide, we change that charge to -1. Okay, so real quick review here. Take 30 seconds to try this problem here. Chromium 6 carbonate. What do you think the formula is? Okay, so it's just really, at first, do we remember what chromium 6 means? Now, if you thought this was the answer here, that's not what the 6 means. So the 6 doesn't tell you how many chromiums are in the formula. The 6 is telling us the charge on chromium. So the 6 is telling us that the charge on chromium is a +6. And so then if we look at carbonate being a 2-, the compound should be overall neutral in charge, and so that's why we're going to put 3 carbonates onto the formula to balance out a 6- with the 6+. And so then, of course, we use the parentheses to indicate the molecular ion where we have more than one of it in the formula. So we have 3 carbonates to balance out our formula here for answer D. Okay, so again, just remember the Roman numeral is a system we use for transition metals. The transition metals in the middle of the periodic table can have a variety of charge states. Most of those metals can form more than one common charge state. What about chromium 3 carbonate? What would its formula be? Well, it would be chromium with a 3+ charge, carbonate with a 2-. So here would be a chromium 2, CO3 3. And so that's going to balance out a 6+ with a 6-. So for a different compound, for chromium that can exist, and this is another common ion of chromium, is the chromium 3+ ion. Okay, so on this slide here, there's a few other anions that are derived off of these oxyanions. And that's where we're adding like an H+ out onto the formula. If you know what acids are, and we're going to name acids in a minute, so it's probably good to start thinking about what acids are. Acids are where you take an ion, like chloride, and you imagine having H+ added to that formula. So if we have HCl in water, we'll commonly refer to this substance, and you probably know its name, is hydrochloric acid. So we'll learn in a minute that this thing here is an acid, and we'll learn how to name it in its categories as being an acid. So things that have H+ added onto them are on their way to being charge neutral acids. In terms of nomenclature, we name things that are neutral in charge as acids. When you get later in the class, maybe even from like AP chemistry, if you took that, or maybe even in high school chemistry, you may have learned that we can call things acids and base properties even if they're charged. Like you can call hydrogen carbonate ion, the HCO3- ion, you can call this ion both an acid and a base depending on the way it behaves in a particular solution. Now, whether or not it behaves as an acid or base doesn't mean we name it as an acid or base. We're going to name it as an acid once it's charge neutral. So we would name H2CO3 as an acid in our nomenclature. But the HCO3-, so once we're neutral in charge, we name it as an acid. And we're neutral in charge when we add 2 H+ onto the CO3 2-. But if we still have a charge, we're still going to have the anion as part of the name. So we're going to go back to that carbonate ion and name HCO3 minus still for being that negative ion. So we're still going to have that carbonate as part of our base name, because we're adding that H plus ion onto the carbonate formula. So we've added 1H plus onto the CO3 2 minus formula. That's why the charge is now minus instead of 2 minus. And so we just add the name hydrogen out in front. So we call that the hydrogen carbonate ion. That's the technical name for HCO3 minus. Some of you guys may have learned this as bicarbonate in high school. How many of you guys learned that as bicarbonate? Just out of curiosity. A few hands. It's kind of funny. The books you guys are using must be really old, because I don't think it's been named carbonate ion systematically by the conventional name for 25 plus years. But the hydrogen naming system is actually much easier, because you just look at the underlying ion. Like, what's SO3 2 minus? Well, we probably remember 4 is the 8, so this is the ite. So this is just sulfite as our base ion name, and then we have 1 hydrogen added, so we just call this hydrogen. Hydrogen sulfite. Now, phosphate is a 3 minus. So if we add an H plus out in front, we only kick that down to 2 minus. So we kick that down to 2 minus when you add that first H plus onto phosphate. So if you were a 3 minus, you're adding H plus to start to neutralize that charge. This would be hydrogen phosphate. Now what about when we add that second? So for the 3 minus ions like phosphate and phosphite, we can add the first H plus and have a 2 minus charge, and we add the second H plus and we still have a negative charge. So if we still have that negative charge, still naming it as an ion, so still basing the name on phosphate, because that's the underlying oxyanion that we're naming. Then we just call this dihydrogen to indicate there's now 2. Remember when we name like calcium chloride? This here. CaCl2, we don't call this calcium dichloride because we don't have to use the di. The only time you see the di added in a ionic compound nomenclature is with these ions here. So if you're putting a di, tri, or a tetra in the name of an ionic compound, probably don't need to be using those prefixes. So again, this is just calcium chloride. It's not dichloride. Even though there's 2 chlorides, you know that there has to be 2, because Cl minus is the only charge possible for chlorine, being a halide. 2 plus is the only possible charge for calcium, being an alkaline metal. And so we know the balance of charge. We know there has to be 2 chlorides for every 1 calcium. We don't need to use the name. There is no calcium chloride versus dichloride. There's only CaCl2, so we just call that calcium chloride. So I'm just making sure we see that the only time we should be using a di out in front of a name of something is in this dihydrogen phosphate, or with the dihydrogen phosphite ion. So we can have this as well. Let me move this down here. If you have PO3, 3 minus, you add 2 H pluses out in front. So you kick this formula down to having a charge of minus. So obviously just dihydrogen phosphite. Now what about K2HPO4? So what about when we actually form then the ionic compound where we pair up the HPO4 2 minus with 2 plus charged potassium ions? So I have 2 K pluses, so I have a plus 2, and I have the HPO4 2 minus ion. And our ionic compound nomenclature system is always, what's the name of the cation? What's the name of the anion? So this would be potassium is the name of the cation, and then hydrogen phosphate. So potassium, hydrogen phosphate. So we don't go dipotassium, hydrogen phosphate. I think it's worth just noting when and why it is that we're using this di, since we could then confuse this into thinking we should call this like dipotassium, hydrogen phosphate. We don't. We're still just cation name, anion name. And then KH2PO4, different compound, different formula, so it should have a different name. And so this one will be potassium dihydrogen. Phosphate. So potassium, one word, dihydrogen, one word, then phosphate, one word. So then there's a few other ions that we just need to learn kind of systematically, just by convention, their names and formula. Cn minus is the cyanide ion. Good ion to avoid because it's very toxic. Hydroxide ion, OH minus. Wait, hold on. OH minus. So this is hydroxide. I think it's illegal for you not to respond to that or something. I don't know. This ion here, this will make maybe a little more sense when we get to like structure and to thinking why we write it CH3, COO minus, kind of trying to tell us the connection of the atoms. Kind of goes like a CH3 and then CO minus like this. But we'll pick that up when we get to chapter 8 later. Sometimes you'll see this written as C2H3O minus. Just where you're combining the two carbons, the three hydrogens, the two O's into the formula. So sometimes we'll write the formula either way, but this would be acetate ion. Then we mentioned this one already was peroxide and superoxide. The next slide has like a summary here, so let's take a look here and just kind of review the ion rules. The key is that the red font are the ions that we should just kind of by convention know how to name, but not necessarily through the direct memorization. Like all the halides have a minus charge. We know that on periodic table placement. And we know oxide sulfide, the oxygen group, 2 minus. We know the nitrogen group would be 3 minus in terms of their common ions. So we can know the charge of those just by knowing how to use a periodic table. Hydrogen, H minus, not very common, but does exist in some compounds. Like we'll see things like calcium with a 2 plus, hydrogen goes minus. So like calcium hydride would be CaH2. So very easy to name with the same system we're building here, calcium hydride for its name. And then we have to memorize the superoxide and peroxide. We have to memorize that hydroxide and acetate. And then we're memorizing those key carbonate, nitrate, phosphate, sulfate names and their formulas and charges. So if we're making flashcards, definitely probably the things in the black font are going to be things we want to just memorize, the chlorate, bromate, iodate. But then hopefully we're just learning the system. You add an O, you just go per. You take an O away, you go ite. You take the second O away, you just call it hypoite without the direct memorization. So like, do we know that IO minus is going to be hypoiodite? I don't think we have to directly like put that on a flashcard to memorize that we can systematically see IO minus and just kind of go IO2 minus, IO3 minus, and then from there kind of build back to what the name of something like IO minus has to be. And then we have the hydrogen oxyanions. And again, those hydrogen oxyanions are just derived off a very simple nomenclature system of if the ion still has a charge, then we're just using hydrogen and the original anion's name. Obviously, these can only exist with 2 minus or greater magnitude charged ions. You don't see the hydrogen oxyanions if you just have a minus charged ion. It is, like, technically it is an acid. It's just not named yet as being an acid. So when we get to acid nomenclature, it'll be for a charge neutral compound. So once you neutralize the charge, if you notice these hydrogen oxyanions still have negative charges on them. So HSO4 minus is indeed an acid, but it's just not named as being an acid until it's charge neutral. So not until we get to H2SO4, where we get that neutral charge, do we systematically name this thing as an acid with the acid naming rules. Does that make sense?
Yeah, but like if you have like hydrogen carbonate, would you say hydrogen carbonate acid?
Not really. I mean, I would say you could say HCO3 minus behaves as an acid, When you get to acids, like anything that in solution can give off an H+, you'll see is called an acid. We talk about that more in chapter 4. So you can call and understand that HCO3- behaves as an acid. It looks like an acid. It just still has a charge, so we still name it as carbonate, if that makes sense. And so we don't use the word acid until we get to a neutral charge. You add the second H+ and go to H2CO3. We'll call that carbonic acid. We'll call H2SO4 sulfuric acid. So we'll see that acid nomenclature system in a couple of slides. So a couple examples. So let's look at the oxide examples first. So what about the formula of potassium oxide? We'll just think, well, what's oxide? O2-. What's potassium? K+. So this should just be K2O. And sometimes I lasso out just to show like the formula wouldn't show the charges. So like K2O would be what we would write for the formula of potassium oxide. Now, what about potassium peroxide? So the peroxide just adds the O, keeps the charge at 2-. 2 pluses, or a plus, so we need 2 of the potassiums to balance out our charge. So we have 2+ with the -2, so K2O2. So I would not actually reduce this to KO. We use the simplest ratio of the ions. Like O2 2- is the formula of peroxide. If you want to see the formula, again, this will make more sense later, but the formula of peroxide looks like this, or the structure of peroxide looks like this. So you can't divide the peroxide ion into just one O- ion. And so an ionic compound is the empirical formula of the ions, not of the formula. So the empirical formula of K2O2 would be KO, but the simplest ratio of the ions is K2O2. So we keep the formula as K2O2 for potassium peroxide. The superoxide goes to minus instead of -2, so we just have KO2. And so these three oxides can actually exist for certain elements. So you may wonder the peroxides and superoxides. These things here, I think it's important to note that they only form with mostly alkali elements and occasionally with alkaline elements. So these only form in fact, I think it's easier if you just imagine they're only really going to form with alkali elements and occasionally with alkaline elements, never with transition metals. So they're an unstable oxide. Transition metals aren't able to form these types of compounds. Now that's helpful because if I give you a formula of like TiO2, where titanium is a transition metal, titanium is a transition metal, then this can't be a peroxide or a superoxide. And that helps you know it just has to be a simple oxide ion. It has to be that just O ion with the 2- charge. And then you know this would be titanium 4 oxide. So titanium 4 oxide would be titanium with a +4 charge, 2 oxide ions. And then that's the only oxide that would actually form with titanium with that charge of titanium. Like we're not going to get titanium peroxide or superoxide to form. That helps us when we see a formula rule out that the peroxides and superoxides aren't going to form with the metals that we don't know the charge of. They're only going to form in cases where you know the charge of the metal. So if I have CaO2, this can't be calcium oxide because calcium has to have a +2 charge. So that's how I know this would be the entire O2 group with the -2 charge, which is the peroxide. So this would be calcium peroxide. So that just helps us then know if you see like MnO2, where Mn is a transition metal, it just has to be the oxide. So that would be manganese 4 oxide, like TiO2, titanium 4 oxide. Okay, so let's get into a few of the other compounds here. So CaCN2, so calcium 2+, Cn-. Cn-, we're just memorizing that as cyanide, so this is calcium cyanide. So this is copper. What's my Roman numeral here for carbonate? Is that copper 1 or is that copper 2 carbonate? So carbonate's a 2 minus, so that means copper has to be a +1 to balance out the 2 minus. So it's copper 1. Carbonate. So again, the 2 isn't indicating the number of copper, it's indicating the charge of copper. So in the last one, what's the charge on zinc? And what's the charge on phosphite? Yep, so phosphite should always be a 3 minus, so that's going to make zinc a +2. So that puts us a 6 plus and 6 minus. Now you might call that zinc 2 phosphite. I don't think that's a bad name, but for some reason we just had said earlier in the cation system that zinc's always 2 plus. So this is just zinc phosphite. Exam questions on this are almost always multiple choice. I don't think they've ever done like a short answer where you have to type in the answer. I don't think they've ever differentiated between zinc 2 phosphite being wrong, where zinc phosphite's accepted. I think you may just come across zinc phosphite and be like, well, what's the charge on zinc as a name? And you'll have to know by convention it's just assumed to be +2 because it's the only ion possible for a +2. So the 2, if you remember, from the transition metal block were zinc 2 plus and then silver plus. It's not in the transition metal block, but you'll see it sometimes without the charge indicated, and that's also lead ion. I don't think we tend to use this a whole lot in nomenclature systems, but sometimes you might see like lead chloride where it's implied to be lead 2 chloride. A lot of times I would want to put the 2 in there, but sometimes we don't use the 2 with lead, but we probably should. But so most of transition metals, we're using Roman numerals. Zinc, silver, the 2 key ones where we're not. Lead's actually not even in the transition metal block. Lead's in the carbon block. But you might see lead chloride used primarily in some lab examples without the charge being indicated. Let's name, I was going to jump ahead, but the way this records, it's actually easier if I just don't jump ahead. This naming system here is almost best if it's the last category because like the things that you can't categorize by being an ionic compound or being an acid or being a hydrocarbon usually would fall into this category. So this slide I probably should have best had as the last category, but we can name it here because this is actually a really simple category where we're just naming compounds that are binary. A binary is just a compound that has 2 elements in any proportion. So we have to have 2 total elements in the formula, but in any proportion. And one of the keys is that we're only going to name the binary molecular compounds this way because the binary ionic compounds are named in a different category. So like NaCl is a binary compound, but it's a binary ionic compound. So we don't name it in this system here. Now again, somebody asked me last time, how do you know a compound's ionic? Ionic compounds have a metal atom and then some non-metal atoms. So if you see a mixture of metals and nonmetals in a formula, that's an ionic compound. So this system here, the first element just takes the name of the element, and then the second element takes its IDE suffix. And so then we use the Greek prefixes, the mono, di, tri, tetra system. And so we would call CCl4 carbon for the first element, and then tetra and the key is that you just use the IDE ending of that second element, so tetrachloride as opposed to tetrachlorine. So carbon tetrachloride. We would call P2O5 diphosphorus pentaoxide. Now, you might see this pentaoxide written as pentoxide. So you'll see sometimes there's some vernaculars used in the name that we're not going to test you on the difference. Like pentaoxide makes sense because you have the penta prefix and then the oxide. And then sometimes you'll see like the tetra oxide would be tetroxide. And the pentaoxide, a lot of times you'll just see it abbreviated or shortened to pentoxide. But that's not a distinction worth worrying too much about. Just recognize that prefix penta out in front. We don't use like monocarbon tetrachloride. We don't put mono when it's the first element. So N2O would be dinitrogen. But we do use the mono for the second element. So this would be dinitrogen monoxide. And you can always come back to like CO2, we know is carbon dioxide, CO is carbon monoxide. So the mono is not used for that first element conventionally within the system. And CrO3 is an ionic compound. So it would just still be chromium 6 oxide. So it's not named in this system. So this would still just be chromium 6 oxide. So you try to think, what's the best category for the compound? And then name it in that category. So this wouldn't be best named in the molecular compound category. You might see some uncommon names for this called chromium trioxide is an uncommon name, or it's the non-systematic name, but the systematic name would be chromium 6 oxide. Okay, so this is the acid rules here. And I think we probably knew HCl was hydrochloric acid. I'm sure you've all heard of hydrochloric acid, whether you knew it was HCl or not, I don't know. But it helps us, I think, if we can remember like that HCl is hydrochloric acid, we probably then learn the rule is for the simple IDE ending ions that have H plus added onto them, then we use the hydro-ic acid system. So we call this hydrochloric acid. And HBr would follow suit because it's just bromide ion, like chloride ion. So bromide would be hydrobromic acid. So it's just the IDE endings go to hydro, root name of the element, then acid. Let's do the ATE endings next. So then if you have chlorate, that ion was added with H+, so now we're in acid form. We change the ATE ending to ic. So chloric acid. And then perchlorates, perchloric acid. So you're just looking, what's the anion name? So chlorate, perchlorate, add H+, neutralize the charge to its acid form. Then we call that ic acid. So chloric and perchloric acid. And so H2CO3, carbonate with H+ added, is carbonic acid. IO4 minus is always the funny one because you put the H+ out in front and it becomes per-iotic acid. I guess it's not that funny, but it's like looks like periodic acid when you say it a different way. But if you know what it is, you call it per-iotic acid. Okay, so then if you have the ITE ending, if you notice, the whole idea of nomenclature is if something has a different formula, it should have a different name. So if you ever find yourself on a test, you could say, like if you have HClO2 and you think it's, let's say you think it's chloric acid, then think, well, what's ClO3 in acid form, HClO3? If that's chloric acid too, we've made a mistake because like two different formulas should have two different names. So if compounds have different formulas, it should be named differently. The way we name the ITE endings is with the OUS acid. So you take chlorite in its acid form, HClO2. This would be chlorous acid. And HClO is derived off of hypochlorite. So this would be hypochlorous acid. If we give you the name of an acid, you can always know it's an acid because it always ends in acid. You know, so like the acid by name are easy to recognize because they end in acid. And then the recognizing an acid, is usually seeing H out in front, followed by some kind of formula that looks like an ion you've learned before. And so like if you look at H3PO4, so you see the H's in front, so this would be phosphoric acid. And then acetate ion. If we write the ion this way, you add the H in front. This would be acetate in acid form for acetic acid. Of course, the thing in vinegar. You'll also see acetic acid written this way. This, again, makes a little more sense once we know a little bit more about structure, which some of you guys might know. But this is another way of writing acetic acid. It's the one weird one where sometimes the H isn't out in front. But with all the others, you're going to see the H in front, then the ion that you recognize out in front. I would prefer the formula, if we put this on the test in chapter 3, where we don't know structure yet, to use this way. As we get through knowing some bit of structure into later chapters, in this form would make more sense later in the course. Okay, and then let's name some organic compounds. There's a tremendous volume of organic compounds you can name. Some of you guys probably had some OChem in high school. Maybe one of the last chapters you did in AP could have been on organic functional groups. We're just going to scratch the surface and name some hydrocarbons, and we're going to name some of their alcohols, and just kind of end it with that. The chapter 2 in your book actually does have a few other compound names. It talks a little bit about things called isomers. We'll talk briefly about that, but we're not going to learn any real sophisticated naming other than recognizing things like methane, ethane, propane, butane as being saturated hydrocarbons, saturated in hydrogen. So a carbon atom is saturated in hydrogen when it has 4 total bonds surrounding it for each of the carbon atoms. So that's why CH4 is the saturated hydrocarbon of methane. 2 carbon atoms, since they're connected to each other, can only bond with 3 hydrogens each. So that takes the formula C2H6. And then propane, we get CH3s on the end, but only CH2s in the middle, because the middle carbon has 2 other carbons it's bonded with. So each carbon can form 4 total bonds, either with other carbons or itself. So we get the formula CH3, CH2, CH3, or C3H8. Butane is the next one that's kind of not really conventionally named, just by a systematic name of being, the saturated hydrocarbon with 4 carbons. So you could probably guess that it's the C4. But the harder part is sometimes, I didn't mean to write the 10, but the harder part is, if you know it's the C4, is knowing how many hydrogens it has. So how would you know that this has 10 hydrogen atoms? I think the simplest way would be, you're picturing propane, but just with 2 CH2s in the middle, and then you're just counting these up. So you're just counting 3 plus 2 plus 2 plus 3 goes to 10. And so then if you want to give the formula of pentane, then you're just looking, okay, the C5H, what is this? Well, I would just be, putting 5 carbons here, and then saturating those with hydrogens. And then counting up the hydrogen. So I have CH3s on the end, CH2s in the middle. So this will be C5H12. Another way of writing it could be CH3, CH2, this is the parentheses, for 3, and then CH2. So you still have 5 carbons, and the CH2s being linear in the middle. This might help as if you're trying to come up with hexane would be the C6, heptane the C7, C8 for octane. Let's get all the way to decane, where that's a C10. If you're thinking of this as CH3, CH2, 8, CH3, it's really easy to count up the CH3s for 6 plus 16, giving you 22 hydrogens. And so these would be the base formula. So if we ask you what's the formula of decane, C10H22. Now for butane and then the other bigger hydrocarbons, they can have this issue of having different isomers. So you could look at butane and say, well, does it have to connect in a straight chain, or could I have something like this, where I have a CH3 here, So you see what I've done is I've just taken one of the carbons and bonded it to 3 different CH3 groups. So I still have a total of 1, 2, 3, 4 carbons. I still have on this formula here a total of 10 hydrogen. So I have 3 hydrogens plus 3 plus 3 plus 1. So I still have 10 hydrogens. Now, we could name this thing differently than butane. We could call one of these things like 2-methylpropane and another one of these things butane, but they're isomers of each other. I just want us to recognize that these are isomers. I don't want us to learn how to name these two differently from each other. I just want us to recognize that sometimes it's called N, or the straight chain butane is a different formula, but still isomeric with this formula here.
So aside from like knowing what isomer is, for example,
Yeah, I would say I want us to recognize that A and B can exist and they're just isomeric, but I don't want us to worry about naming that other isomer B and what its systematic name would be. So I just want us to recognize that they're different compounds, different structures. Probably means they have different properties. Maybe not drastically different properties, but maybe their melting points and boiling points are different from each other. But I'm not going to worry about systematically naming compound B. I'll just still call that thing butane. If we give you a formula of that and say, what's its name, you'd be like, well, it's an isomer of butane. So it's just C4H10 or butane. With the alcohols. Alcohols are where you take any of those hydrocarbons and replace just one of the hydrogens with the OH, IO group. It becomes a crime at some point if I keep doing that, I think, on my part. But instead of CH4, it's CH3, and then the OH group here, and this would take the name methanol. I prefer writing this way as opposed to just writing the formula CH4O. Both are technically legal formulas for methanol, but I think the CH3 and then the OH group does kind of tell you that you're replacing one of the hydrogens with this particular functional group. And so ethanol, kind of the same way. I might write this C2H5 with the hydroxyl group then, or C3H7 with the hydroxyl group for propane. So this would just be methanol, ethanol. We could call that 1-propanol, and again, it becomes kind of a distinction of we're not going to worry too much about the number. I would just call that propanol. You could differentiate this from, I think this is on the, you really don't have isomers with ethanol or methanol, right? Because you're just putting the hydroxyl in a different position, but it's still the same molecule. So like if we put this group here, it's still ethanol. It's this exact same molecule. So you only get this difference of isomeric positioning of the hydroxyl group when you get the propanol and beyond. But again, we're not going to, like you might see some old examples if I haven't been careful of removing them, but you might see some cases of, well, what's the structure of 2-heptanol? Don't worry about knowing what the 2 means. It means it's on the second carbon. It's not that hard, but we're not going to like test you on that part of the nomenclature system. Slide from 1-propanol versus 2-propanol. So we could learn how to name these numbers for which number of the propane chain the hydroxyl group is on. But for what I want us to recognize is just that these two are both propanol. That they're isomers again. I want us to recognize that they're isomers. I want us to recognize that isopropanol is the common name of the middle of the 2-propanols. This is isopropanol. This is N or 1-propanol. That I want us to recognize that they're isomeric. Don't worry about the numbers. Like I don't care if we learn how to name these numbers on them. You'll learn that in OChem. So I just want us to learn that you can have the hydroxyl group on different carbon atoms when you get to propane. The second half of the last section, chapter 2, does go into some other details on like naming those branched hydrocarbons. Don't worry about that part. Just worry about, and you'll see on the practice exams, you won't see any examples of those nomenclatures. In fact, that's new in the new edition of the textbook. It wasn't even in the older versions of the textbook. So just some review here. We did the periodate. So this was the HIO4 acid we named earlier. We did carbonic acid of carbonate. So this is H2CO3. What's the name of H2SO3? So like our purpose here is formula to name, name to formula. So what's the name of this? Sulfurous acid. H2S, I signify as an acid, so just H2S really doesn't behave in solution kind of like HCl and HBr does, so it really maybe isn't described always as being an acid, but we can name it in the category. Just so I like to say that here. So that just means we're looking at sulfide as being the underlying ion. So what would you call this here? So this would be like hydrochloric acid. So this would be hydrosulfuric acid. So for categorizing, so when we look at a compound, think, is it an ionic compound? If it is, name it as such. Is it an acid? If so, name it as such. Is it a hydrocarbon? If so, name it as such. Is it an alcohol of a hydrocarbon? If so, name it as such. Is it none of those? And it's probably a binary molecular compound. So this here is in that binary molecular compound nomenclature system. So this would be dinitrogen, tetroxide, or tetraoxide. We did pentane already, C5H12. The key is really, I think, the 5 is the easy part. The 12 is slightly trickier, but not that tricky. It's just sketch out the 5 carbons if you have to, 4 bonds to each carbon total. Do you guys know the name of this pretty easily? Octa, octane, octanol. And so, again, you may wonder, C8H18 is octane. So that'd be CH3s on the end, 6 CH2s in the middle. So sometimes these questions are a little tricky. So try to look at this part for about a minute. Try to see if you can spot the misnamed pair. So if we look, some weird music coming from this side. It sounds like some epic theme music going on. Like, makes me think we're 3 minutes ahead of where we are. Sodium perbromate is right. Calcium phosphite, that is phosphite, that is calcium. This is the right 2 plus 3 minus balancing of the ion, so that's right. Nitrite, this is nitrate. So this would be copper 1 nitrate, so that's the one that's wrong. Silver carbonate, you may have thought where's the 1, but silver's the one that we know by convention is plus, so we don't have to use the 1 for silver. So silver carbonate is the proper name. Ammonium, and then chlorate for ammonium chlorate as being right for E. So another name formula, we can do this one together. In fact, it looks right off the bat like it's the first one. That's sulfurous acid, not sulfuric acid. So that one's incorrect. Well, it's incorrect, so it's the right answer. Like, that's a good reminder. Sometimes you look for the incorrect answer, you cross it out, and you think, okay, that's not the right answer. It is the right answer to the question because it was the incorrect one, so maybe cross out here. Chlorous acid, ClO2 is chlorite. Ites go to us acid, so that is correct. Acetic acid, that's right. Hydrobromic, that's right, and phosphoric is right. And lastly, we already looked at this one, octane, octanol. So hydrocarbons. The key for nomenclature is if you right now are sitting here thinking this is easy, just do a little bit of practice with it, do some of the daily quizzes. The nomenclature always looks easy at first, and then there's always little nuances with it. But give it some practice, make sure it sets in, and that you remember it come exam time. We've done most of these examples already, so that is 1 and 2, and we are heading is about it for chapters 2, chapter 3 on chemical reactions on Monday. So we'll head into chapter 3 when we start class on Monday. Have a great weekend.